we're going to continue to look at our investigation of slopes of curved objects. That's our real focus here when we're talking about the derivative and differential calculus. One of the things that you'll see slope related to is what's called rate of change. So we're going to spend a little bit of time at the beginning of this section just talking about different ways that rate of change comes up in real context, and then we'll see what that has to do with slope, and then again what that has to do with calculus. So the question about how fast do you drive, when someone asks you that, they could mean one of two things. They could mean what was your average speed over the course of a trip, which is this interpretation, taking 2.5 hours to drive between two particular mile markers. And so we could report the average speed, but during a trip, especially a 2.5 hour trip, you probably were going pretty fast sometimes and pretty slow other times. In fact, you may even stop somewhere along the way, and none of that detailed information is reflected by the average speed. The time where you see an instantaneous speed or an actual speed is when you look down at your speedometer and see what it says, your actual speed is at that time. Or if you were in the unfortunate case of getting a speeding ticket because as you pass somebody with a radar gun, they clocked you at a particular speed. They don't care what your average speed was over the whole trip. They only care about what was your speed at one particular moment. And notice that those two scenarios really are not mutually exclusive. It's very easy to have an average speed from one report, but then be going, an average speed of like 50 miles an hour, but the fact that you could have gone 70 or 80 miles an hour at some point is not out of the question. The calculated average speed, we just take the total change in distance divided by the total change in time. So if we went from mile marker 201 to 57, that's Shippensburg to Pittsburgh on the Pennsylvania Turnpike. That's 144 total miles, and over 2.5 hours, that comes out to be 57.6 miles per hour. Notice that the units here, miles per hour, is reflected by the top units and the bottom units. So whatever the top units are per whatever the bottom units are, that's how the units for the rate of change will always be calculated. But you might notice that this calculation actually looks a lot like the slope calculation, and that's not a coincidence. So this change in distance over change in time is really exactly the same thing as the calculation we did before, delta y, change in something over delta x. Remember, we used the delta, the triangle, for change. So if y measures distance and x measures time, then delta y is change in distance and delta x is change in time. So in a scenario where the y coordinates represent distance and the x coordinates represent time, then this miles per hour calculation that we're doing to get the average speed is actually the same thing as change in the y over change in the x, which is slope. So if I had a graph that had those y coordinate for distance and that x coordinate for time, then the slope is what the rate of change corresponds to. Let's look at this in the setting of some business problems, because this is more what will happen in this class, more than distance and time. But no matter what your x and y units are in a problem, you can do the same kind of calculation. So for example, if you have a certain revenue from generating, selling x objects, so in these problems, x is always, I'll write x here. In these problems, x is always the number of items that are being sold. Then the y coordinates here are measuring revenue. And so if we want to know what the average rate of change, or the rate of change of revenue is, we would need to do the change in y divided by the change in x. So the change in y would be the change in revenue of production changing from 9 to 12. So that's x equals 9. Where you're changing from producing and selling 9 items to producing and selling 12 items. If your production changes that way, then so the change in revenue from the 12 item level to the 9 item level to the 12 item level is given by just this difference. And again, in terms of a graph, this is a change in y coordinates. And so we would get $36. That's how much revenue changed. We have $36 more revenue from selling 12 items than we got from selling 9 items. The average rate of change is the change in y over the change in x. So again, that's something we can interpret as slope later on. That's the change in revenue, which we saw was $36. And the change in the x's is 12 minus 9. And those are widgets, whatever we're selling. So we get 36 over 3. Which is 12. And again, the units are dollars per widget or per item. So when we have a rate of change, it's always measured in something per something, y coordinate units per x coordinate unit. So that's what the rate of change would mean in terms of the revenue function, or in terms of any function. So in general, the average rate of change is just a change in y over change in x. So this is formally what it looks like. If you have a value of two values of x from a to b, then this is your change in y coordinate over change in x coordinate calculation. And we call that the average rate of change of the function from a to b. And we do notice here, again, I said it before, but we note that this is exactly the same thing as finding the slope between 2 points on the curve. So all the stuff we said before about slope is now going to be something that we can apply to the idea of rate of change. Now, what we're really interested in is not the average rate of change, but we're actually interested in the instantaneous rate of change. So this is the difference between saying that I averaged 57 miles an hour on my trip to Pittsburgh and saying that when I passed the cop with a radar gun, I was going 78 miles an hour. The 78 miles an hour that I was going at a particular time is my instantaneous speed as opposed to my average speed over the trip. So the way we calculate this is actually very similar to what we did in the last section, where we say we know how to do average rate of change, and so if I want to find my instantaneous rate of change, I'm just going to calculate the average rate of change over a very, very small interval. The reason for a small interval, just like with the example of the radar gun in the cop, when he clocks me going 78 miles an hour, that's actually doing a calculation based on the radar is doing a calculation of my average rate of change over a very, 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 very short time period, over milliseconds, because my speed can't change very much over a millisecond of time. So if you calculate my average rate of change over a millisecond of time, then that really is a very good approximation of my actual rate of change. So that's what we're going to do, and you'll see the letters in here, the x equals a and x equals a plus h. We're not going to go through the formal derivation of these rules, but if you look in the book or you look on other websites, that's what you'll see. The idea is to take the average rate of change between 2 points, like we were doing before, but you want to imagine the h being incredibly, incredibly small, something very, very close to 0, like a millisecond or whatever the units are.